Good day, class, and welcome to another lesson in organic chemistry. In our previous lesson, we treated alkenes, and now we are on alkynes. And we said that alkenes and alkynes are aliphatic hydrocarbons, that is straight chain hydrocarbons. We said alkenes have single bonds between carbon atoms. Alkenes have double bonds between carbon atoms, while alkynes have triple bonds between carbon atoms. We also said that alkynes form a homologous series of unsaturated hydrocarbons with carbon-to-carbon triple bonds. We say alkynes have a general molecular formula, CnH2n-2. The unsaturated carbon is sp3 for alkanes. The carbon atoms in alkanes are sp3 hybridized. The carbon atoms of alkenes are sp2 hybridized, while the carbon atoms of alkynes are sp hybridized. The unsaturated carbon in alkynes are sp hybridized, comprising of 1 sigma bond and 2 pi bonds. The hybrid orbitals are as far apart as possible, with bond angles of 180 degrees, giving them a linear shape. This is what we mean here, if you can recall. This is your ethyne. You have your hydrogen here. So the bond angles here is 180 degrees. And the shape is a linear shape. Okay, we also went further to say that alkynes are the most reactive among the aliphatic hydrocarbons. Alkynes are the most reactive. And this is so due to their high electron density as a result of their pi electrons. Meaning that alkanes are the least reactive. Alkenes are more reactive than alkanes. Alkynes are more reactive than alkanes and alkenes. We went further to see the synthesis or the preparation of alkynes. We said ethyne can be obtained industrially from methane at 1500 degrees Celsius, and the reaction condition there is 1 second. It gives us our ethyne and hydrogen gas is given off. Also, ethyne can be obtained from the industry by the hydrolysis of calcium dicarbide. This calcium dicarbide, when it's being hydrolyzed, that is calcium dicarbide reacts with water as such. This is hydrolysis. It's going to give us our ethyne plus calcium hydroxide. That's how it gives us in the industry. We also said another method by which we obtain alkynes is from the laboratory, and the main method there is by dehydrohalogenation of halogenoalkanes, that is removal of hydrogen halides from halogenoalkanes. We took an example of 1,2-dibromoethane as such. Take a keen look at your screen. This is a 1,2-dibromoethane. We acted in the presence of alcohol and potassium hydroxide. We boil it. It is going to give us our ethyne plus hydrogen plus potassium bromide plus water. That is how we said we obtain alkynes from the laboratory. For our lesson today, we're going to be looking at the physical properties of alkynes. And talking on the physical properties, we realize that alkanes range from gases to liquids, then to solids. Alkenes range also from gases, liquids to solids. But alkynes exist only as gases and liquids. This is due to increase in van der Waals forces. The first three members of alkynes are gases and the rest are liquids. This is due to increasing van der Waals forces with increasing relative molecular mass. They are insoluble in water, but soluble in nonpolar or organic solvents. If you remember from when we started treating alkanes, we say alkanes are insoluble in water but soluble in nonpolar or organic solvents. And these organic solvents include kerosene, petroleum, and so on. Petroleum, diesel, all of these are organic solvents. Then you come also to alkenes. You realize that alkenes too are insoluble in water but are soluble in nonpolar or organic solvents. Alkynes do same. They are insoluble in water but soluble in non-polar or organic solvents, which means that this is a similarity between the aliphatic hydrocarbons. All the aliphatic hydrocarbons are insoluble in water but soluble in non-polar or organic solvents. The next subheading there is reactions of alkynes. Alkynes undergo mostly electrophilic addition reactions due to the presence of multiple bonds. This takes place in two stages, and this is known as a double addition. The first stage producing an alkene and the second stage producing an alkane. The addition takes place twice as much as those of alkenes. The addition reactions, what we mean here is the addition reactions of alkynes, occur as twice as those of alkenes. The first reaction type we're going to look at is reaction with hydrogen. Alkynes react with hydrogen to yield either an alkane or an alkene, depending on the number of molecules of hydrogen. Like we said, they undergo double addition. When alkynes react with one molecule of hydrogen, they yield an alkene. If they react with two molecules of hydrogen, they yield an alkane. This reaction takes place in the presence of nickel catalyst at 150 degrees Celsius or platinum catalyst at room temperature. But now we realize that even at that, if special conditions are applied, such as using palladium catalyst, whose activity has, we said, if special conditions are applied, such as using palladium catalyst, whose activity has been reduced by barium sulfate. By barium sulfate, like you can see from the second equation, a time reacting with hydrogen in the presence of palladium catalyst whose activity has been reduced by barium sulfate at room temperature, it is going to give us ethene. Which means here that when this activity has been reduced, the activity of the catalyst has been reduced, the reaction cannot proceed to give us an alkane. The next reaction we're going to look at is reaction with hydrogen halide. Like we said, under alkanes, with their reactions with hydrogen halide is being determined by Markovnikov's rule. And Markovnikov's rule states that in the addition of hydrogen halide to a multiple bond, The multiple bond could be a carbon-to-carbon double bond or a carbon-to-carbon triple bond. Markovnikov's rule states that in the addition of hydrogen halides to a carbon-to-carbon double bond or a carbon-to-carbon triple bond, in an unsymmetric alkene or alkyne, the hydrogen atom attaches itself to the carbon atom linked with the largest number of hydrogen atoms. And this rule also applies to alkynes. You can see our first product produced there is chloroethane. Chloroethane, that is obtained from the reaction of ethyne and hydrogen chloride, gives us chloroethane. Chloroethane reacting with another molecule of hydrogen chloride is going to give us, take a keen look at the first reaction there, it's going to give us 1,1-dichloroethane. 1,1-dichloroethane, indicating that from the second step of the reaction, whereby chloroethane reacts with a molecule of hydrogen chloride, the hydrogen atom attaches itself to the carbon atom having 2 hydrogen atoms, and the chloride ion attaches itself to the carbon atom having 1 hydrogen atom. The next reaction is going to be reaction with halogens. Ethyne reacts explosively with chlorine in the presence of UV light by free radical mechanism to yield carbon and hydrogen chloride. However, if the reactants are mixed in the presence of a catalyst of aluminium trichloride, ethyne undergoes addition reactions. Like you can see on your screen. See right in the product, you realize changes in the bonds from triple bond in ethyne to double bond in 1,2-dichloroethane, and that 1,2-dichloroethane reacts further with another molecule of chlorine in the presence of an acid catalyst, which is aluminium trichloride, is going to yield us 1,1,2,2-tetrachloroethane. The fourth reaction we are going to look at is the reaction with water. Ethyne reacts with water using dilute sulfuric acid and mercury sulfate as catalyst. We say ethyne reacts with dilute sulfuric acid and mercury sulfate as catalyst. The water molecule is hydrolyzed as such. This is how the water molecule is being hydrolyzed. You have your water molecule, it undergoes hydrolysis. It's going to give us this. This is how the water molecule is being hydrolyzed. Okay. We said the water molecule is hydrolyzed as such, hydrogen ion and hydroxide ion, which acts electrophilically to produce ethanol, which undergoes rearrangement reaction to give ethanol, which means ethanol undergoes rearrangement reactions to give us ethanol. Ethanol is a carbonyl compound. In the hydrolysis of ethyne, in the hydrolysis of ethyne, ethanol is first produced and later ethanol. The ethanol and ethanol are in dynamic equilibrium with the ethanol predominating. We say in the hydration of ethyne, ethanol is first produced. Ethanol is first produced. As you can see from the reaction there, ethyne plus water in presence of dilute sulfuric acid and mercury sulfate as catalyst is going to give us ethanol. This ethanol undergoes rearrangement reaction to yield us ethanol. The ethanol and ethanol are in dynamic equilibrium, with the ethanol predominating. The phenomenon whereby a pair of isomers are in dynamic equilibrium to each other is referred to as tautomerism, and the isomers are known as tautomers. In this case, the isomers here are ethanol and ethanol, and these isomers are known as tautomers. And the next reaction we'll be looking at is oxidation reaction. Oxidation reaction, that is, how do they react with oxygen? Ethane burns in oxygen to form carbon dioxide gas and water. As you can see from the reaction there, you have that. The next reaction is polymerization. Ethane, when heated in the presence of a complex nickel catalyst, polymerizes to benzene. We say ethane, when heated in the presence of a complex nickel catalyst, polymerizes to benzene, like you can see from the reaction there. That's it. You see our reaction. That is how ethane polymerizes in the presence of nickel complex catalyst and heat. It's going to give us a benzene. Remember, from the first class we said benzene is an aromatic hydrocarbon. The next thing we're going to look at, the next type of reaction, is formation of metal carbides and dicarbides. Alkynes with triple bonds at the end of the chain are called terminal alkynes. Because of the high electron density, there is the tendency for the hydrogen atom at the tender end to be displaced or replaced by copper or silver ions. When a terminal alkyne is put in a test tube with ammonical copper 1 chloride or ammonical silver nitrate, and this is heated, a reddish brown precipitate of copper 1 dicarbide or a white precipitate of silver 1 dicarbide is formed. Where one hydrogen atom is replaced, a carbide is formed. Where two hydrogen atoms are replaced, a dicarbide is formed. The reaction is carried out by dissolving the silver 1 or copper 1 salts in aqueous ammonical solutions. Example. Let's look at the example on the board. Examples of terminal alkynes are, you have ethane, butane, propane. We have ethane, butane, propane, and pentane. Those are examples of terminal alkynes. And we said that dicarbides are formed when a terminal alkyne is put in a test tube with ammonical copper 1 or copper with ammonical copper 1 chloride or ammonical silver nitrate and heated. And when this is heated, a reddish brown color, that is a reddish brown precipitate of copper 1 dicarbide or a white precipitate of silver 1 dicarbide is formed. like you can see there. Like you can see on your screen there, the dicarbides. For example, we use silver ion reacting with ethine is going to give us silver 1 dicarbide, and there we have a white precipitate. Then if we have to have a carbide, we are going to react our ethine or our terminal alkyne with 1 molecule of silver ion or copper ions to give us our carbide. And now we are going to look at the test for aliphatic hydrocarbons. Test for aliphatic hydrocarbons. This is based on how to identify the various aliphatic hydrocarbons. That is, how can you determine that a given compound is an alkene, alkane, or alkyne? And how can you differentiate between these 3 aliphatic hydrocarbons? How can you say that this compound I'm using or this compound given is an alkane or alkenes or alkynes? Alkanes, when reacted with bromine in the presence of tetrachloromethane in darkness or with bromine water, there is no reaction and the reddish brown color of bromine is not decolorized. You say the reddish brown color of bromine is not decolorized. If you can remember, have a recall of the reactions of alkanes. We said alkanes react with halogens in the presence of ultraviolet light, which means that in darkness, if ultraviolet light is not present, then the reaction doesn't occur. And even if light is present, the reddish brown color of bromine does not disappear. That is, alkanes do not decolorize bromine or bromine water. Alkenes, when reacted with bromine in the presence of tetrachloromethane in darkness or bromine water, the reddish brown color of bromine is decolorized, forming 1,2-dibromoalkane. For example, you have your example there. As you can see on your screen, just try to watch keenly and study. Okay, we have our alkene there reacting with, the alkene there is ethene reacting with bromine in the presence of tetrachloromethane and darkness. We're going to have 1,2-dibromoethane, and the reddish brown color of bromine is decolorized, indicating the presence of a multiple bond, and in this case indicating the presence of ethene. Terminal alkynes, when reacted with ammonium copper 1 chloride or silver 1 nitrate and heated, a reddish brown precipitate of copper 1 dicarbide or white precipitate of silver 1 dicarbide is formed. You can see, there you have your example. Propane reacts with ammonium copper 1 chloride. It's going to yield us our copper 1 butane with 1 ion, that is a carbide. And we go further to say that alkynes also undergo the reactions test of alkenes. Take for example, the reaction of alkenes with bromine or with bromine. We said that alkynes are also going to decolorize the reddish brown color of bromine. Same with alkenes. But now, you realize that alkanes and alkenes show no reaction with ammonical solutions. Alkenes decolorize the purple color of potassium permanganate, producing 1,2-diol. That you can see from the example there. Propane reacting with acidified potassium permanganate to give us propan 1,2-diol. Alkanes show no reaction with potassium permanganate. Thank you and see you next class. In our next lesson, we're going to begin with aromatic hydrocarbons, and that is benzene. Thank you and see you next class.